I'm Syed, a senior security engineer at CME Group. Today's talk is more like an update call on post-quantum migration. So it's more or less like what's happening, what's going on, what's the crack really. So if you have your calculators on you, I would recommend just put them away because it's not going to be very mathematical talk, so touch wood. I would like to start off with frequently asked questions that I get as a cryptographer every day from my friends, colleagues, peers. And trust me, some of them are actually quite smart. The first one is actually my favorite. Are current cryptosystems cracked? If any of those questions seem like that you wanted to ask as well, so just raise your hand and I'll make sure I answer it through the talk. So that's not a straightforward answer to that. Are current cryptosystems cracked? Well, we'll see what the answer is through the talk. The next one is post-quantum cryptography safe? Well, that's again a tricky one. We'll need to know about that in a bit future. Why do we need to migrate, and what happens if we don't migrate? Again, they're all fair concerns, and it makes a lot of sense for someone who doesn't want to migrate. Is quantum threat real or made up? That's an interesting one as well. How long do we have before our data is breached? This is from one of my friends who likes to do his things last minute, and that makes sense. Why for your quantum I use 128-bit key? Well, that's a fair point. Somebody knows what they're doing, so yeah, 128-bit key is good. Why for your quantum? What do we need to do for post-quantum migration? Well, again, this is going to be something that I'll be covering through the talk, so bear with me. Before we move further, I think I'd like to highlight the importance of this unique relationship between security and assumptions. Before I moved into cybersecurity, I thought everything was 100% secure. But trust me, there's no cyber-physical system that I can say is foolproof and is 100% secure. So it's mostly your assumptions, or if I use another word called scope. So you have to scope out your application, the practicality of attack, and all those things. And then you think of a system as secure, insecure. For example, let's start with the first information processing standard, also known as DES, or data encryption standard. In 1977, when it came as a standard, the recommendation was 56-bit key size, right? As of that time, they did some assumptions, right? They scoped out what they were looking for. But in the following year, it was cracked, 56 hours. Next year, cracking time went down to 22 hours, right? Now, after that, we have Randall, that's also known as AES, one of the variants, Advanced Encryption Standard, and the recommended key size is 128, 192, and 256 bits. And well, it's amazing because it's 23, 24 years, and AES is still the current standard. It's strong. It's not broken yet. Until, as of now, I'm talking. I don't know if it's broken, but yeah. Last time I checked, it wasn't broken. So, another unique relationship that I would like to emphasize is assumptions and recommendations, right? Now, I talked about assumptions. Anyone can make assumption. This morning when I was walking to Europe, I was like, oh, it's going to rain. Well, nobody's going to believe if I told, oh, there's going to be storm this evening. But if you go to BBC weather, you're going to have a little bit of confidence there, right? So between assumptions and recommendations, we mostly tend to look at standardizing bodies or organizations that are expert in that field. For example, in security, we have National Institute of Standards and Technology that is considered the holy grail. So they kind of do the heavy lifting. They have labs, they have experts, they have research wing, and they kind of do the heavy lifting and they provide recommendations on everything related to security. So this special publication, 857, I've shamelessly stolen this table from there. So you can see any key size less than 112 bits is not encouraged. So it's just for legacy use. If you have something encrypted, you can use it to decrypt it. But anything after that, do not use 112. If you really want to go for it, that's your call. But they encourage you to go for 128 bits or higher than that. So again, this is also a recommendation through 2030 and beyond. Now you might ask me, okay, going back to that question, I use 128-bit key, right? I'm strong. I don't need any security, right? I'm good. So why 128 bits? And for example, we're talking about AES, which is a symmetric algorithm, private key algorithm. Why 128-bit key? How did they make this assumption? Well, there are several ways to do that calculation. But what I did was I looked at blockchain. So when you make an assumption, as I said, we need to look at the practicality, right? How easy is it for an attacker to do an attack, right? Now, people do talk about supercomputers, but I swear I have never seen a supercomputer in my life. I don't know where it is, but I haven't seen it. But this one is a screenshot from blockchain network. People who are into cryptocurrencies, they know that we are having accelerated hardwares, we have FPGAs, we have ASICs that are actually being used to do, crypto mining. In other words, like we're calculating hashes. And when I talk about the figure, so this screenshot is from 6th of September, and it was like 6.7 million terahashes. If I write in numeric, it's 10 to the power 18, right? That's a big number. So that's how many hashes are being calculated per second in a blockchain network, right? Now, for 128-bit key, you have 2 to the power, my apologies for calculators. You can bring them out, if you want to do the calculations. But yeah, 2 to the power 128 is the possible combinations that you'll have to go through to find the actual key, the right key. And then it sounds like a bit practical. Okay, not that practical, but if I had authority, I can use this blockchain network. Instead of calculating hashes, I can calculate encryptions, right? So for every encryption, that's one try, right? And then, you feed in the network and see, is that the right key or not? So I'm going to skip the basic mathematics. It's literally just converting into hours and years and seconds. And the interesting part is the third last line that is highlighted in 17.9 billion years is like estimated time that you would need for this network. That is a blockchain network fully equipped with hardware, accelerated hardware and FPGAs and ASICs to crack that key. Now, a little Googling, NASA website says 3.7 billion years since the age of the universe, right? Now, it's roughly 4.8 times the age of the universe you would need to break that key. Some people might say, okay, you know what? There's a 50-50 chance you wouldn't have to go through all 128, 2 to the power 128 combinations. So, okay, divided by 2. Okay, take the average. It's still, if it's twice the time of age of universe, it's massive. It's technically impractical. And that's how assumptions are made. So if somebody needs twice time of the age of universe to crack that key, I'm going to assume it's secure, right? Now, coming back to that question, that's my favorite. Why fear quantum? As I said, it's twice the age of universe. I'm safe, right? That's not that simple. In cryptography, we have two main types. It's private key cryptography, also known as symmetric, and then we have public key cryptography, which is asymmetric. So far, I've been talking about a symmetric, which is less affected by quantum. And the reason for that is, for symmetric algorithms or private key algorithms, the security is based on the strength of pre-shared key. So you have a shared secret or key that the sender and the recipient both need to have it, right? And it depends on that. So the easiest or most applicable attack is brute force or the exhaustive search attack, right? On the other hand, we have public key algorithms in which you have public and private key. Apparently they have massive keys. They're like, 2048, 4096 RSA keys if somebody has worked with them. Now we have a public and private key pair, and their security is based on hard mathematical problems. What are hard mathematical problems? They basically have trapdoor functions. Trapdoor functions are easy in one direction and harder in the other. If I was to give an example, it would be like if I was to tell you multiply two numbers, P and Q, easy. But if I was to tell you, calculate the factors from a big number, you'll be like, okay, where's my calculator, right? Let me do it. So for example, in RSA, we have 4096 or like 2048-bit key. That's basically P and Q, a multiple of two prime numbers. That's your RSA key. And the problem here is quantum computers can crack it. So if I give you an example of private key first, let's go in the same flow. So Grover's algorithm, it's a quantum algorithm. It's also known as quantum search algorithm. So the impact on symmetric key or private key cryptography would be, the attacks would be a little bit speedy, right? So you can work around by increasing the key size, and you're safe. And that's one of the reasons cryptographers are not worried about symmetric key at all. They're like, okay, we'll increase the key size. I was using 128, I'll use 256-bit. I'm good. But with public key cryptography, it's not that simple, right? You're going to keep increasing the key sizes, but its main target is the trapdoor function. Now, with Shor's algorithm, you can actually solve those trapdoor functions, rather it's based on prime factorization or discrete logarithm. And in that case, it kind of is RSA and elliptic curves are both susceptible to this one. And if anybody's into PKI or public key, infrastructures or, TLS comms, everything, digital signing, your bank cards, everything is relying on RSA and elliptic curve. So if that's gone down, that's a bit of a problem, right? Workaround for that, again, thanks to NIST and researchers who have been working hard, there are quantum-resistant algorithms, now also known as post-quantum. So quantum-resistant, quantum-resilient, post-quantum, it's the same thing. So lattice-based or hash-based algorithms are basically not relying on trapdoor functions, and they could be a good substitute to actually replace the current algorithms. Well, coming back to those FAQs, and one of them was, is quantum threat real or made up? Right. Well, I'll leave the final decision to you, but I'm just going to spit out some facts that I think are a bit dodgy. So, number one, quantum industry is turning into a multi-billionaire industry at the moment. There are more than 200 companies working in quantum software, quantum processor manufacturing, and all that sort of stuff. So there has to be something real, right? They're not making things up. Now, we know about this little, flexing and this competition going on between these corporate giants, Google, Amazon, Microsoft, IBM. Every other day we hear like, oh, we've got a stronger quantum computer. On the right, the picture I have added is of a Sycamore quantum computer. And the claim they made is that it can do, or it can solve the problem that would take 10,000 a year on the fastest supercomputer. As I said, I've never seen a fastest supercomputer. There could be, but that could be an assumption, right? In 200 seconds. That is fast, right? So there's company Atom. I think that has the strongest quantum computer, 1125 qubit. IBM Condor is the runner-up. Again, it's a bit tricky domain because quantum computers have a lot of error rates and stuff. So there's some quantum computers with better error correction and stuff. So there are lots of options, but a lot of work need done there as well. Another interesting one is China-Russia quantum link, right? Now, there is a quantum-proof link, as said again. Now, I don't know the assumptions on what assumption they're saying it's quantum-proof, but they have done some experiments, and it's quantum-proof, right? You can go Google it. It's called, it's working with quantum satellite called MOSI, something like that. Another interesting one is mysterious laws coming up. So you might have heard UK recently introduced that if you have a quantum computer that is 34 qubit or higher than that, you cannot export it. And it's not only UK, France, Spain, Canada, and actually there are 42 members of the Vesnar agreement that are also looking into imposing it. Last night I checked, US also had some controls over quantum export, but that's just the starting. I think that brings me to the question, how long do we have? Right. Well, it's a tricky one because you can push these things to the last minute, but technically I think it's already too late. This cloud technology, easy access to everyone, like in this room, we're all cloud users. At the moment, if I just minimize it, there it is. I'm using Google Drive. It's a cloud space. That's how easy it is. Now, all you need is to just grab the data, just put it in the cloud and wait for quantum computers to come into life. On the other side, if you're talking about state actors, on a state level, country level, your data might be, you don't even know they're taking your data and they already might have a strong quantum computer to decrypt it. So there are two sides of this. Now, officially it's called Harvest Now Decrypt Later attack, and I think it's just a time game. If I was you, I would say we don't have much. Let's move to post quantum. Now, on that note, again, coming back to National Institute of Standards and Technology, NIST, they've done the heavy lifting for us. Post-quantum algorithms always existed. They were around with different names. But in 2016, NIST published a report saying that RSA is vulnerable and blah, blah, blah. And they started a post-quantum standardization process. And since then, it kind of narrowed down from 69 candidates to 26 in round 2, and then to 15 in round 3. And from there, they got 4 candidates which have actually been standardized. So we have Crystal's Kyber, which is a key encapsulation mechanism. In easy words, an encryption mechanism. Crystal's Dilithium, Sphinx, and Falcon, they are digital signatures. They're more or less like signing algorithms. So Sphinx Plus is not based on lattice. It's on stateless hash-based technologies, but it's just like a backup. So You might say KEM, the encryption algorithms, are not that many, because as we discussed earlier, private key cryptography is not that badly affected, right? But they're still considering backups for that as well, because we would prefer moving fully to post-quantum, right? So in round 4, they had 3 alternate candidates for KEM. That's BIKE, Classic, Macallis, and HQC. And we have 3 drafts from the standards just published last month. We're waiting on the 206, that is Falcon. And then, the alternate candidates could be next year. They're not high priority. So, yeah, again, it's a recommendation. You don't have to use them. They've published the standards. They've done all the hard work. They ran public competitions. Community has, gone in, broken them. A lot of actually research, an interesting one. Let me share it with you. So there were a few post-quantum, I think it was Psych, that was broken by Belgian researchers. And they broke on a normal laptop in 2 hours. So that was a post-quantum candidate, and it was going very good with that. I think it went to second round or third round as well. But then recently another paper published in Kyber that it's broken, but then there were a few false claims made on it. So Kyber officially is not broken yet. That I can attest. That brings me to migration plan advice. Well, I might not be able to give you migration plan advice here because every organization, every business is different, right? I know companies that still use Excel sheets to store their keys, right? So if you're in that stage, don't bother, right? Like, you're good. So there are plenty of resources available. You can actually check your PQC readiness. You can check the state of, on what level you're at. The picture you see on the right side is actually from Gartner. That's my personal favorite. They kind of started from 2022, which was a good time to start, but let me tell you, it's not too late. Just follow the steps and you'll be grand. It's just kind of a little bit of convincing you need to take. Our data is not safe. Let me tell you that. Well, that brings me to my last slide and one of the interesting questions again, but I do not trust post-quantum. And to be honest, I'll raise my hand on that. I do not trust post-quantum either. But is there a way out? Do you have a solution? Do I have a solution? I don't think so. I think our best bet would be to go hybrid. So hybrid would be elliptic curve and Kyber, and that is already available. You can have the support in Google Chrome. I think it was Google Chrome 24. Firefox, AWS. Cloudflare has done a lot of good stuff on that. So they have actually done testing because a lot of people have concern regarding performance. So they have done a lot of testing on performance. Another interesting tool is Cloudflare PQC agreement tool. So if you thought you have activated that, a crypto suite in your browser and you're safe, you can just go to that link. It's in the bottom left corner, and it will let you know if you're post-quantum secure or you're still using the classical one. So I think just try to become friends with post-quantum, right? To be honest, like, it's time if you're into development, if you're into software industry. libOQS is really popular. Like, it's been around for a while. I have used it myself. I think it's part of Linux Foundation now. And try to play around. If you can break it, even better. We know we don't need to use post-quantum, right? libcrux is a bit new library, and I think my personal favorite is a security site. It's securitybsides.com is run by Professor Bill Buchanan. He's, I think, professor at Edinburgh University. It's very easy to understand, like, better explained than me. So maybe go there and, play around with a little bit of post-quantum algorithms. What you see on the right, if I have time, I'll quickly run through. So you're not changing much. You're actually just using Kyber to do the encapsulation for the random secret that is generated. Rest of it is done by elliptic curves on the key distillation on both ends. So it's pretty. You can say you can get the best of both worlds, right? If post-quantum is not safe, you still have classical. If classical is broken, you have post-quantum. So as of now, I would say go hybrid. Follow the migration plan, follow NIST standards, stay in touch, maybe get professional services to get analysis of your business, that what level of PQC readiness you're at. And I think, fingers crossed, we shall be good. And on that note, I would say a massive thank you to everybody for attending, and BSides. Thank you.